This lesson is about approximating the binomial distribution with a normal one. Why do I need to do that? So what do I know is that finding cumulative probabilities on a binomial distribution is time consuming. We've seen that. But finding cumulative probabilities on a normal distribution is much faster. We use table of values and we use our calculators. And I will notice that in some cases, the binomial distribution graph resembles the bell shape. We are going to touch on this more on the next slide. So these three make me wonder, is there a way to estimate cumulative probabilities on a binomial distribution by approximating it to the normal? And the big question I have, the binomial distribution is discrete and the normal is continuous, so how am I going to account for that? These will be the questions that we are going to answer in this lesson. Let's look closer into the binomial distribution. We will explore it further and we'll start by looking at the variable x, which is binomially distributed with n equals 20 and p equals 0.5. 20 is the number of trials in a binomial experiment. So I have 20 trials, with p being probability of success. So I have 50% chance of success. X, the variable which is binomially distributed, measures the number of successes within 20 trials. So I can have 0 successes, 1 success, 2 successes, up to 20 successes. This graph shows the probability of successes. So, for example, for x equals 8, the probability of getting 8 successes within 20 trials is going to be about 0.13, seems to be. That's how I interpret this graph. We can't have a probability bigger than 1. That's why my y-axis stops at 1. So we're going to look closer into the shape of the binomial distribution for different n's and p's. Why we do that is that from the previous chapter you might have noticed that it's quite difficult and time consuming to find probability, cumulative probability on a binomial distribution. For example, here to find probability of x being bigger or equal than 11, I will need to calculate probability of x being 11, 12, 13, 14 and so on up to 20 and add them up all. It's quite time consuming. And I'm looking for ways to approximate cumulative probabilities on a binomial distribution. That's why I need to study the shape of the distribution. And you might see where I'm going, because we've just learned the normal distribution, and you can see that for this n and p, this shape resembles the bell curve. However, I need to take this carefully because the distribution that I have here is discrete and the normal distribution is continuous. So I'll see how I deal with this later. First, let us look at the shape. So for a p equals 0.5, a 50% chance, I see that the curve follows a bell curve. What if I change n, the number of experiments? So if I change n and I have 24, 26 and so on, it is still similar with a bell curve. What if I have n very small? The probabilities get smaller. For example, for n equals 6, I can have 0 successes, 1 to up to 6 successes within 6 trials, but the curve still resembles a bell curve. Right, let's look now what happens if I change p. Let's assume I have the probability of a success become smaller and smaller and smaller, and see how it's clear that the shape is not anymore a bell curve. So there are cases when I can't approximate the binomial distribution by a normal. Let's see what happens if p becomes very big now, close to 1. So if p is 0.5, see, we said that it's closer to 0.5 is symmetric, but if I go on the other side with p very big, it's not a normal anymore. Okay, let's make p small and see what happens if I keep p small but I make n large. So if I carry more and more experiments, I'm looking at probability of successes, see how the shape becomes normal. resembles normal. I stop here with P at 50, but I can continue. So that suggests that if P is big enough, then the curve will resemble a normal distribution curve. Let's see if I keep P n big and I make P also big. So of course, when I get to 0.5, I know it's going to be symmetric. How about on the other side? It becomes symmetric again. But see, I will need to make, because P is very, very big, close to 1. It can be bigger than 1, right? But it's very, very close to 1. Then when n would become bigger, the shape will be closer and closer to a normal distribution. So we'll need to establish some conditions for n and p such that I can approximate the binomial distribution with a normal. After doing that, I can calculate probabilities on a normal distribution because these are easier to calculate, and then draw conclusions about probabilities, cumulative probabilities of the binomial distribution. So the question arises, what are the conditions when I can estimate a binomial distribution by a normal one? It is clear for our movie that n needs to be large. But how large does it have to be? Because in the case when n is 50, there are some values, like extreme values for p, when that doesn't resemble a normal distribution. However, if I go not close to 0.5, but a bit lower, it will still be a normal distribution. So the condition that it's accepted widely is that n needs to be large enough to ensure that np is bigger than 5 and nq is bigger than 5. Let me remind you that we are on an x binomial distributed with np, where p is the probability of success and q is 1 minus p is probability of a fail. It makes sense to put both conditions because see, when p is 0.95, q will be 0.05, and when q is here, p will be on the other side. So practically with these conditions, I cover both ends for p to be either small or big. So these are the two conditions when I can estimate a binomial distribution by a normal, and we need to learn this by heart. Whenever I use such an estimation, I need to check that these two conditions are true. As an example, here, in my case, n is 50 and p is 0.95. And we said that x is binomial distributed with 50 trials and 95% probability of success. If you want, you can think of it as having a bag, and in the bag you have 50 balls or marbles, and you have, or let's take 100, it's easier to think of it, and then you have 95 marbles white and 5 marbles black. So you have a probability of, and x measures the number of white if you draw 50, if you have 50 withdraws with replacement. Can I estimate that by a normal distribution or not? So let's look at NP and let's look at NQ. So NP is 50 times 0.95 and NQ is 50 times 0.05. This one is 2.5. It's not bigger, it's smaller than 5, therefore I can't estimate by a normal. And you can see from here, it's exactly this example, so it doesn't resemble the normal distribution curve. I didn't check this one because that one is bigger than the other one. So if one of them is not fulfilled, the other doesn't matter. We have seen that in the case when x is binomial distributed np, and when n times p is bigger than 5 and n times p is bigger than 5, then we can estimate x by a normal distribution. Sometimes I use the letter xc from x continuous to remember that actually the new distribution that I get is different from the previous one. It's a good estimation, but it's still different. Let me check in my case here if the conditions are met. As you see, NP 25 times 0.68 is 17, is bigger than 5, and then Q 25 times 1 minus 0.68, this is Q, is 8, which is bigger than 5. So the conditions are met for an estimation. In the exam, you need to write this, and you need to write that the number is bigger than 5. That's your reasoning. Otherwise, if you just leave the number, nobody will see that you actually know what you are looking for. We are going to answer now the last question on my first slide. The binomial distribution is discrete, and the normal distribution is continuous. So how am I going to account for that? If you look at probability of x being 14, for example, x equals 14 is here, so probability of x being 14, it's about, I will estimate it's about 0.07 maybe, or 6. I can calculate it exactly, it's just an estimate from the graph. However, if I'm looking at the probability of x on the continuous distribution to be 14, and that's my continuous distribution, how useful is a notation? It's a different distribution. We've learned that on a normal distribution, which is continuous, probability of x being exactly on a point is 0. But that would be on the continuous distribution true for all points, for 0, 1, 2, and if I add up all this probability, is going to be 0. So it doesn't work like that. So how am I going to calculate to estimate probability of x being 14 on the binomial distribution? Where am I going to find this on the normal distribution? So imagine you have the normal shape here, estimating this distribution. In order to understand that, we can focus at 14. And we need to look a bit of the way we represented that. Basically, we said that on the binomial distribution, probability of x being 14 is the height of the graph, of the bar, because that's how we represent it always. When we look at probability of x on the continuous, and we want to see what's around 14 on the continuous distribution, probabilities are actually areas. So the problem with understanding that came from our representation as probabilities on the continuous distribution being areas, but on the discrete being the height of the bars. We can, however, think of this bar in a different way. If this probability is the height of the graph, we can think of a rectangle of the base 1 coming from 13.5 to 14.5, and we can think of the probability on the binomial distribution as being this area. Now, maybe my graph is not very accurate, but as you see, some of this area will go out, some of the area will go in, so practically this area we can estimate is the area under the normal distribution. Therefore, to calculate the probability of x equals 14, or to estimate it from the binomial, is the same. We'll say it's the same. We can estimate it as probability of your x continuous being between 14.5 and 13.5. So we take an interval of the length 1. And therefore, we'll estimate it by the area under this graph. That is called continuity correction. So we say that continuity correction. So we say that we apply continuity correction when we estimate probabilities on a binomial graph with probabilities on the normal graph, which is continuous. You might remember from the previous lesson that it doesn't matter if we put less equal or less than, because probability on a point on a continuous distribution is 0, as we mentioned before. So when we want to estimate probabilities, cumulative probabilities on a binomial distribution, what we can do, we can look if these conditions are met to see if we can estimate this distribution by a normal distribution. And when we calculate probability on, or we want to estimate probabilities on a binomial distribution, We estimate them by using the continuity correction. There is only one question left. Okay, so we know now when can we estimate, we know the continuity correction. What will be the mean and the variance of the normal distribution? That question should be very simple, because we say that we have a good estimate, we can estimate well x by xc. It means that the mean of the binomial should be the same as the mean of the normal, and the variance of the binomial should be the same as the variance of the normal. So we know that the mean of the binomial is n times p, and we know that the variance of the binomial is npq. This means that this should be the parameters for the continuous one. So we have the continuous one as being normally distributed with np and npq being the variance. Remember, I taught you that it's always useful to write the variance and the standard deviation square so that you don't remember when you use the standard deviation in a question. Let us try this question. You can stop the movie and try it by yourself. Probability of x smaller than 9. If you think of the binomial and 9 is somewhere here, if you want probability and 8 is here, if you want probability of x being smaller than 9, you want to include everything, including 8, but not include 9. So this will be the same as probability of xc on the normal is less than 8.5. And it doesn't matter if I put less or I put less or equal. In the second question, I want to include 9 as well. So that's going to be probability of x on the normal distribution is smaller than 9.5 or smaller or equal. Now I want probability of x being bigger than 12. So 12, 13, 14, and so on. 12, 13. If I want x to be bigger than 12, I don't want to include 12. So that's going to be probability of xc bigger or equal than 12.5, or just bigger than 12.5. It doesn't matter again. I can put bigger or equal. Now in the next question I want to include 12 as well. So that's going to be probability of xc bigger or equal than 11.5, so that I include 12. How about this one? It's about, if I don't want to include 13, then I need to start from 13.5. If I want to include 15, then I need to stop at 15.5. Here is one solved example from your textbook. You might try by yourself, please. Stop the movie, and after it, continue and check your solution. And here is another question that I want you to try in the same way.